Uh, Everybody, hello. Do you have my voice? Can you hear my voice?
I can hear you, sir.
Okay, very well. Thank you for your participation in this conference, ELECO 2021. Please let me introduce myself briefly. My name is Davut Ertekin, and I'm an assistant professor in electrical and electronics engineering department of Bursa Technical University. Now we are going to hold the session 28 of ELECO 2021 Power Electronics 2. For this session, we have 5 amazing papers from the authors of Zonguldak, Bulent, Ecevit University, California Institute of Technology, United States, Yonnet Research and Development Center from Turkey, Gaziantep University, İskenderun Teknik University, and Istanbul Teknik and Eskişehir Technical University, all from Turkey, and finally paper from University of Tabriz, Iran. At the first stage, no, I'm going to hold this stage to paper ID 33, multi-variable modeling and system identification of an interleaved boost converter from Ridvan, Keskin, Ibrahim, Alishkan, and Ersin Dash. Please consider that you have only 15 minutes for the presentation and 5 minutes for the possibly questions and your valuable answers. Stand is yours, please.
Okay, sure. Hi, I am Ridvan Keskin from Bulent University, a PhD student at university. I will present our paper about multivariable modeling and system identification of a two-leg interleaved boost converter. I divided my presentation under 4 main sections. First, I will explain the DC-DC converter circuit and its controller function. After that, I will explain small signal modeling of the converter with its disturbance effects. Then simulation and experimental studies in here will be presented. Introduction section. Our main goal is to obtain the frequency responses of the input voltage and load current disturbances in two-leg interleaved boost converter. So, to increase the robustness of, increase the performance of any linear controllers to be synthesized, we will learn about the frequency range of these disturbances. In here, this converter circuit, input voltage and load current are depicted as the main disturbances. Because if you suppress the frequency components of around the resonance amplitude of the system disturbances with the controller, the robustness of your controller will be increased. Here, this converter circuit, interleaved boost converter two-leg. Here, the converter consists of 2 active, 2 passive, and a low-pass filter. The parasitic resistance of inductances, switches, and capacitors are included in the nominal modeling using small signal modeling method. The load current in here and load current is here, and load current disturbance is here. They are separated from each other. The load current disturbance is depicted as a separate current source. The input voltage disturbance in here is the AC component of the input voltage source. The PWM signals and gate signals of the converter can be seen in here. According to this PWM signals of the converter, 4 operating modes can occur or happens. Then in here, according to the gate signals of the converter, yes, 4 different operating modes happens. Here, inductance currents, capacitor voltage represent state variables in here, while input voltage and load current in here represent disturbance states, B matrix. A matrix is the state of the system. B matrix is the disturbance matrix of the converter. C denotes the state-to-output relation vectors, and E denotes the disturbance to output relation vector for each number of the converter operating modes. A, B, C, and E matrices are obtained from derivative expressions according to operating modes of the converter. Then the content of matrices can be seen from this equation in here: A1, A2, and 4, and A3. Then these matrices are averaged according to the cycle value of each operating mode. In here, D1, D2, D3, and D4 represents operating modes of the converter. Then the content of the matrices can be seen from this figure image. Expressions are decomposed in here DC and AC components. Finally, they are converted or transformed from state space to continuous transfer functions using this classical control equation. Finally, nominal and disturbance transfer functions can be seen in this equation. These are obtained as second order transfer functions. Looking at these equations closely, it is seen that the denominators of the disturbance transfer functions are equal, so their roots are at same frequencies. The open loop system identification scheme, classical, and its process can be seen in this figure. Here, we use the frequency-rich PRBS signal to excite the input signal to get a good frequency response of the models. The desired frequency responses are obtained by adding PRBS signal in here to input voltage and data cycle of the system. After output or input voltage are collected, it is transformed to frequency domain, and desired frequency response can be obtained. In here, applied PRBS signal to gate signal and its power spectral density distribution can be seen in this here. Since the bandwidth of the circuit or converter is about 120 Hz, we applied a frequency-rich PRBS signal up to 5 times this value in here. I mean, it's nearly 600 Hz. We obtained the appropriate amplitude value of this PRBS signal by trial and error process. Finally, simulation result sections. RX, RMAX, and BG models, Bakobi junction models from linear parametric system identification methods are preferred for model estimation. In this figure here, frequency response from control signal to output voltage can be seen. Here, these three approaches have similar frequency responses, but RMAX and BG models are second order, while RX model is a fourth order one. Then here, input voltage to output voltage disturbance transfer function. Like the previous one, these three approaches have similar frequencies, and they have same model orders. Experimental results section. A DSP card from Texas Instruments is used to apply the gate signals and read relevant data from the converter. In here, two-level IBC circuit and gate signals, gate driver circuit, or DSP card, RLI for input voltage changes. I used this relay, load resistance, mains power supply, and TLP gate oscillators. This DC power for TLP gate drivers. The exact values of the components used in this experimental study were measured using LCR meter in here. Then I updated the values of the passive components in simulation study. Here, the output voltage in here and PRBA signal obtained from the converter can be seen in this figure. Since the real-time signal sampling rate of the DSP card is limited, healthy data was obtained up to a certain frequency. It's nearly 50 Hz because the sampling time of the DSP card is 0.01. Here, frequency response from gate signal to output voltage can be seen in this figure. Although the estimation is good at low and medium frequency, in here nearly 100 Hz, the estimation accuracy decreases as the sampling frequency limit approaches in here. Then conclusion section. The frequency response from gate signal to output voltage can are obtained. The small signal models of the two-leg interleaved boost converter are obtained by modeling load current disturbance as a bifurcation parameter or as a separate current source. The frequency response of the converter are verified using linear parametric identification approach. Then the estimated frequency responses validate the mathematical models over wide frequency range, but around the resonance frequency, estimation of these models decreases. That's it. Thank you very much for listening to my presentation. If you have any questions about the study, I can answer them now.
Thank you for your quick presentation. Now I want to ask to all of the friends and colleagues in this session and all of the attendees, and if they have any question, please. You can raise your hand by the Zoom. So it seems there is no comment from the audiences. So I have some of the questions that I kindly ask you to respond to me. Please show me the figure 1, the first figure that show the interleaved boost converter. Yes. Okay. It seems you have had a very deep mathematical analysis for the obtaining the equations, and it is very nice paper. But here I have a question. As you know, the internal resistances of the components is very critical parameters in finding the gain of converter or any other transfer function, for example, as you done in this study. As I can see here, you had entered all of internal resistances for the components, but for the power diodes, DE1 and DE2, I can't see any internal resistance. Can you let us know what was the reason?
It's the parallel resistance of the inductances are nearly 1.5 resistance, nearly. Okay.
You know, if you cannot neglect from the internal resistance of switches, you should consider the same parameter for the diodes.
Parallel resistance of the MOSFETs or active switches are nearly 0.06. I think I remember.
Do you remember the label of the power diode? Which diode you use?
Yeah, 0. Because the resistance
normally the internal resistance of the fast recovery diodes or SIC or a GAN type of the diodes normally is low, but most important parameter for the power losses calculation is the forward voltage of the diodes that sometimes reach to 106 or till to 2 voltage, and this can really challenge your equations. So for the next slides, please rapidly can show me. I will have some of the questions. The next slide, the next one, the next. Yes, yeah. For example, G nominal. What is the G nominal? The relation between output voltage and input
That's cycle
voltage?
to output voltage. That's the cycle to output voltage.
Okay.
PWM signals to output voltage.
Very good. It will be nice to show this part for also for GD in and GDR. Also, you can show. And finally, I want to ask you, what was the reason that you used the changing frequency approach for the interleave boost converter instead of changing the duty cycle and fixing the switching frequency? Normally, we show in all of the buck boost or buck boost converters that also me, I'm working especially on buck boost converters, all kind of power converters, and normally I fix the frequency and only change the duty cycle based on the change of the input voltage or output loads. But it seems in your paper you are changing the frequency.
No, I use fixed frequency PWM signals.
What was the frequency?
1000 hertz.
100
kilohertz.
100 kilohertz.
Yes.
Okay. Okay. What was the your prototype power?
Power 200.
200. Okay. Very nice. Thank you for your presentation. I suggest you for your next studies, you can input, for example, the voltage and currents of the power diodes. Also for the inductors and capacitors and power switch. All of these parameters are very interesting to know more. And also you can show the input voltage and output voltage where we couldn't find what was the input voltage in your structure. But overall, thank you for your presentation. Now, in turn, I will see that we have a paper with ID 84 entitled Design and Application of a Novel Dimmable Lighting Control Unit with Active Power Measurement via KNX protocol from Yonnet, if I don't mistake, Yonnet Research and Development Center from Turkey. Can you see, please, in the stage paper number 84?
Hello, I'm Mr. Chairman. Can you hear me?
Hello, I can hear you and ask you, please open your camera.
Okay, this is, let me turn on my lights. This is a little dark here.
Okay, so we are going to see your slides.
Hello.
Very nice.
Can you see my screen? Let me start my presentation.
Please don't forget, you have 15 minutes to present and 5 minutes to possibly questions and responses.
Okay. I am trying to share my screen. Can you see my screen?
Yes.
Okay. Thanks for the audience for joining the session. Hello everyone, I am Ahmet Furkan Ergan, working as an embedded system engineer at Yonnet R&D Center. And Dr. Kemal Sarioglu, the second author of the article, is the R&D advisor of our company. The topic of our study is design and application of a novel dimmable lighting control unit with active power measurement via KNX protocol. In this study, I will tell you about the design methodology of a dimmable lighting control unit compared to the valuable theoretical and experimental information intensive presentation so far. I will talk more about the design methodology of a commercial product. Then let's start. Here is our presentation outline. At the beginning of the presentation, I will give some short information about our company and focus area. After that, I will tell you why we start this study and what is our motivation for designing this product. Next, I will give information what is KNX and what we need to get KNX certificate for product. At next stage, I will tell you design methodology of our universal dimmer, and at the end of the presentation, I will explain the stage of the product that emerged as a result of the study. Who we are, Interleaved technology is a registered trademark of Yonnet Bilişim. Yonnet Bilişim is our official company name, but we known as Interleaved technology market. We are an innovative technology company who developing software and hardware products for building automation market. We are also an R&D center approved by the Ministry of Industry and Technology. As we develop KNX products, we are a member of the KNX Association and are also approved training center. Our Interleave brand is a global brand that is on sale in 75 countries. We also have offices and employees in some of these countries, and in some we launch our product through local dealers. In here you can see a part of our product. We have a very wide product family under the Interleave brand. In our building automation product line, we have touch panels, switches like this, software solutions, guest room management systems for hotels, gateways like DALI IR AC, home server, power devices like power supply, dimming units, relay devices, and sensors. Our touch screens, these touch panels, are the first in the building automation market and have contributed greatly to the direction of the industry in domestic market and the awareness of our brand in this area. We have many more products than here. Those who wish can more detailed information by visiting our website, interleaved.com. What is our motivation for starting this study is identifying the need for a new dimmable lighting control unit in the building automation market. The multi-platform control released in this study is not yet available in any product in the global market, compatible with both KNX, IP interface, and conventional switches. Lack of AC dimmers with control over IP interface in the market. There is some IP-based LED dimmers in the market, but no AC dimmers. And increasing awareness of end users about energy consumption and savings due to rising energy prices. KNX is an open standard for commercial and domestic building automation. It supports twisted pair, power line, IP, and RF physical transmission medias, and defined by the standard EN 50090. Connect is a former name for the KNX, but we are using KNX now. KNX is first and only international standard in the world for home and building control. Manufacturers who want to develop products in the KNX standard must comply with the rules published by the KNX organization as a member of the KNX Association. These standards provide relevant information in all areas, from the data types to communication physical layers, from creating a product database to the failed assembly stage. We did some literature research for the concept, design, and requirements of the dimmer module. This study that shows the most similarity with the keywords zero cross detection, AC dimming techniques, AC load type detection, Paralink MOSFETs were examined. It was seen that the AC dimming techniques were customized according to application. Zero cross detection in AC control circuits plays an important role in determining the switching angle. Loss can be of different characteristic, and the switching techniques they need can vary. AC load type detection is an application-specific topic, so there are not many sources in the academic literature. The issue of the parallel operation of channels is largely related to synchronous operation performance of electronic switching elements located in different channels. So, what is dimming? Dimming means reducing the output of the lamp or lighting fixture. For the AC loads, there is phase cut techniques for reducing mean output power. These are a leading edge control for resistive and capacitive loads and trailing edge control for inductive loads. So you can ask why we can't use the same technique for all loads. Actually, we can use both technique for resistive loads because they are linear loads, but not for the others because of their characteristics. Since capacitive loads acts like a short circuit while being charged, they will draw a lot of current when they are derived with high voltage. The opposite is true for the inductive loads. For AC dimmers, we are using MOSFET switches for control voltage. Since the main voltage we want to control is AC and MOSFETs have body diodes by default, we need to use bidirectional switches as the switching elements. At the beginning of the design, we first determined the mechanical, electrical, and functional requirements according to the market needs. After that, we determined our system architecture. We decided to use 3 boards in this design because of mechanical and isolation considerations. Here are specs for this product. This coming marketing department from our company. At the lowest level, we have dimming control board to drive the loads. These boards have isolation between the main controller boards and AC line between these channels. On top of the dimming control board, we have main controller board, which is controlling whole system. Communication interfaces and analog digital inputs are located in these boards too. At the top, there's a user interface board so that the installer can test the installation with this buttons and feedback LEDs. As you can see in the main controller scheme, the communication interfaces are directly connected to the main controller, these ones, but not dimming modules because the channels have high voltage connection at the dimming channels. So there's a need for the isolation for users and devices safety. You can see that each dimming channel has its own microcontroller and AC power supply. This 4 dimming channels is similar with each other. On the dimming module scheme, we have some blocks for protections like short circuit and overload protection and temperature protection. Each dimming channels have power measurement circuits separately. For the communication with main controller, all dimming channels have optical isolation between dimming controller and there's the optical isolation layer between this MCU and this MCU. Zero crossing detection block is very important for synchronizing with AC line. We cannot detect zero crossing point properly. This will cause flickering in the lights. Since the computer-based zero crossing circuits doesn't require many components, this design has been considered the most optimal solutions in terms of simplicity and cost. The zero cross signal obtained in the simulation is shown in the figure left. This sine wave is our AC input voltage, and square wave is our zero cross circuit output. The biased zero cross circuit also connected to microcontrollers on analog to digital converter channel for the load presence detection and load type detection. The load presence detection feature has been added in order to prevent the device from the driving and creating a dangerous situation when the output is idle. Sorry. In the simulation studies and experimental studies in here, on the prototype board, it has been observed that the shape of the signal change in the same way in the absence of load. So
you have totally 5 minutes, please.
Okay. Another criterion aimed to be realized in the study in the detection of the load type, the main issue here is to understand whether the load is inductive or not, because driving an inductive load with the wrong technique may cause malfunctions in the device and make device unusable. We can also detect load type which same zero crossing circuit. The idea behind this that the switch off responses of the loads are different. You can see here capacitive and inductive loads switch off responses. It has been observed that inductive loads starts to be driven at the 0 point and cause voltage increases in the supply line when they are suddenly switched off while there is voltage on the loads. However, such a behavior was not observed in the capacitive and resistive loads. For the active power measurement, we are using active power metering ICs because of the ADC of our microcontroller is used to perform other functions. We have isolated communication, as I mentioned before, between dimming microcontroller and main microcontroller. We need isolation because there is 220 volts AC on the dimming module and 30 volts DC lines on the main controller board. Because of this low and high voltage used together in this device, we need to isolation between them for the KNX standard. In the standard, this isolation level is set at 4000 volts. And short circuit or current protection. This is for when we current flowing through the switching elements and crosses their limits. It must be turned off very quickly to protect them. A protection circuit independent of the microcontroller has been designed for this because we need a minimum delay for this switching off. Next slide. Our main microcontroller board design. The main control board is mostly digital boards, unlike the dimming board. This part of that performs the main task on this board in the main control firmware. What we have on this board is power supply for microcontroller, physical communication layers, USB hardware for the firmware upgrade, digital and analog inputs on this board too, and links for dimming channels, links for user button and feedback LEDs, and embedded web server for configuration and control. This is a firmware side actually. And our firmware architecture, firmware studies were carried out on the DIMM microcontroller, DIMM input, the input module microcontroller and main microcontroller. Our firmware architectures vary according to needs and workload. Since the main microcontroller performs a lot of tasks, the architecture here is wider. You can see here. While the DIMM microcontroller have a simpler architecture because they work as slaves. Since the firmware created the analog and digital inputs will work in a fairly low feature microcontroller, it must be a fairly limited code structure. For this reason, the code of this microcontroller has minimal and efficient structure that will perform operation directly. In parallel with the PCB design studies, mechanical design studies were also continued, and mechanical design in accordance with the target criteria was revealed. After that, once the PCB design were completed, we produced prototypes of these PCBs for functional testing. In order to perform the functional test, of the products, a test panel was produced with different kind of loads, and basic tests such as load tests and temperature tests were made on this panel. At the end of the study, we have realized first pilot production of the product, and we are currently planning electrical tests in accordance with the Electronics standard. This is our end product, our universal dimmer, and dimmable lighting control unit has been developed. It has a KNX interface, IP interface, and it can control lights with conventional switches. That's all I'm going to tell you. Thank you all for listening.
Thank you for your presentation, Mr. Ahmet Furkan. Now, I want to ask to all of panelists and attendees if they have any question. Please raise your hands if you have any question. So I have some of questions. Did you try this prototype for any type of inverters?
No, actually, it's not working like an inverter for this power level. Inverter type dimming controllers using much more bigger.
I know. Did you see Z source type of inverters already?
No.
I have a suggestion for you. Since I saw your experimental results from the your prototype, this is very appreciated for the Z source kind of inverters. I suggest and invite you to see this type of inverters and test this device for that kind of inverters, where these inverters we can directly convert the DC voltages to AC voltages, and normally through a modulation index that I can find that your prototype can support that. So you can do very amazing studies there. So I invite you to test the prototype there. I have some questions, but we have very limited time and other presentations. So I thank you and ask you to close your screen. And now, in turn, we have paper ID 55, level shifted pulse width modulation-based battery state of charge balancing method for single phase cascaded bridge multilevel inverters from Gaziantep and Iskenderun Technic universities, please.
Hi everyone, can you all hear my voice?
Yes, we can brightly hear.
Okay, let me start then. My name is Fatih, and I'm from Gaziantep University, and the title of my paper is level shifted pulse modulation based battery state of charge balancing method for single phase cascaded H-bridge multi-level converters. And we will start with an introduction to explain the role of battery storage systems in the power systems, and then we will investigate bidirectional power flow control, and later on we will talk about our proposed HOC balancing control method, and we will present our simulation results, and finally we will give you our concluding remarks. So as you know, variable intermittent behavior of renewable energy sources cause some economic and environmental problems in power systems. And that's where battery storage systems come into play, and they are able to store the overly generated energy and to supply that energy to power system when it is needed. And we can say that battery storage systems give some sort of a flexibility to power systems. A battery storage system includes two main subsystems. The first one is power conditioning system, and the second one is battery management system. And power converters are able to serve both subsystems by controlling the power flow and operating the batteries in an efficient manner. And multi-level converters are great candidates for such systems due to their reliability, improved power quality, and fault ride-through capability. And these multi-level converters can be used in large-scale grid-connected applications, residential battery storage applications, and vehicle-to-grid applications as well. So there are three types of multi-level converters, three main types of multi-level converters. The first one is direct current multi-level converter, and second one is flying capacitor, and the last one, and also the one that we used in this paper, is cascaded H-bridge multi-level converter, and it consists of series connected H-bridges. We can also call it as cells, and a battery pack which is connected in front of each cell. And we have two main control aspects in our system. The first one is bidirectional power flow control, and the second one is, and our proposed methods belongs to here, state of charge balancing control. But before investigating these controllers, we need to look at the need for SOC balancing control in cascaded H-bridge multi-level converter-based battery storage systems. As we said before, cascaded H-bridge-based multi-level converters employ separate battery packs, and there could be some differences in there could be some electrochemical differences between different battery packs. And when we combine these two facts together, we can say that there could be some SOC variations between battery packs. And the results of these SOC variations are some partial charge or discharge of some batteries, and this causes reduction in battery storage systems efficiency. And the other disadvantage is different DC voltages caused by different SOC values between battery packs. And this results in distorted output waveform at the output of the multi-level converter. And that's why we need SOC balancing. In our paper, we used level-shifted pulse width modulation to trigger our semiconductors in our cascaded H-bridge multi-level converter system. In the literature, as it's known, the power is distributed unequally between different H-bridges of multi-level converter in level-shifted pulse width modulation technique. And this could be viewed as a disadvantage, but we used in SOC balancing, our SOC balancing methods, and take it as an advantage. So to sum up in this paper, a level-shifted PWM-based SOC balancing method is proposed, and bidirectional power flow control is held as well. So let's talk about the overall control diagram and circuit representation of our battery storage system. As you can see, this is cascaded H-bridge multi-level converter configuration, and it's connected to single-phase grid via a coupling inductor. And when we measure the grid's voltage and currents, we converted into DQ frame components and used these components in bidirectional power flow control. And the results of power flow control is fed into SOC balancing control, as well as estimated SOCs of these battery packs. And output of SOC balancing control is used in level-shifted PWM, and triggering signals are obtained to semiconductor switches. Okay. Let's talk about our bidirectional power flow control system. We used current control in DQ frame, and that's why we can control active and reactive power simultaneously and independently. Simple PI controllers are employed, and the formula to determine the current references are given below. And this is the block diagram of the bidirectional power flow controller in the Q frame in a single phase system. And as you can see, active and reactive power references are fed into the system. And at the end, we obtained some voltage references that we used in SOC balancing control. So this graph shows the carrier waveforms in level shifted PWM for a single phase 7-level cascade H-bridge multi-level converter. In a 7-level converter, there are 3 H-bridges, note that. And as you can see, the carriers are in phase, but they are displaced in magnitudes. When we used level shifted PWM to obtain outputs of each H-bridge, this is the graph that we obtained. And as you can see, the conduction time of each cell is different. So we can say that current flowing through battery packs, each battery pack, are different as well. And we use that property in our advantage to balance SOC of each battery pack. This is the zoomed view of level shifted PWM carriers. As you can see, there are different levels to obtain different conduction times for each cell. And this is the flow chart of the algorithm that we used. Let me explain it briefly. And first of all, we initialize the carriers to each cell randomly, and then sort SOCs in ascending order. And depending on batteries are charging and discharging, we just give the carriers, the corresponding carriers to corresponding cells. For example, if the batteries are charging, and if the cell with the highest SOC gets the lowest conduction level, and cell with the lowest SOC gets the highest conducting level, so that we can charge more the cell with the lowest SOC. So let's talk about our simulation results. As we said before, a single phase grid connected 7-level cascaded H-bridge multi-level converter based battery storage system is designed and developed. Performance of bidirectional power flow and SOC balancing controller is analyzed. We just give some dynamic changes in active and reactive power in both directions. And we initial unbalanced SOCs are used, and balancing performance of the proposed controller are investigated. These are the general design parameters for our simulations. As you can see, the single phase grid voltage in terms of RMS is 220 volts and grid frequency is 50 Hertz. The carrier frequency that we used is 2 kilohertz. And we used lithium-ion batteries with a rated pack voltage of 120 volts and a rated capacity of 5.8 ampere hours. And as you can see, these are the initial SOC values for each battery pack. These values are chosen very close to each other, but different, as you can see, to reduce the simulation runtime. But if these values are displaced with a high rate, this method is also works. This is the output of the bidirectional power flow controller, active reactive power tracking performance. And as you can see, active and reactive power references are successfully tracked throughout the process. This is the zoomed view of grid current and grid voltage between some very small timing interval. And as you can see now, grid voltage is stable as we fixed, and the grid currents can adapt to changing active reactive power values. This is the output of cascade H-bridge multi-level converter. As we said before, since we used 3 H-bridges, we get 7-level output waveform at the outputs. And this is the state of charge balancing performance of the state of charge balancing methods. And as you can see, the initial SOCs are different. The yellow line represents the average SOC between these three battery packs. Initial SOCs are different, but they become equal after almost 4.5 seconds with the help of proposed SOC balancing methods. These are the last two graphs of our work. The first one is battery voltages, and the second one is battery currents. And it's visible that but both battery voltages and currents are different under unbalanced SOC conditions. However, when SOCs are balanced, they become equal as expected. So to conclude, we designed a single-phase electronic multi-level converter-based battery storage system, and a level-shifted PWM-based SOC balancing method is proposed, and along with a bidirectional power flow controller. And it's verified that proposed SOC balancing method is tested under unbalanced conditions, and balancing is achieved, and active reactive power flow control also successfully obtained. So these are my references, and that's it. Thank you.
Thank you, Mr. Fatih, for your good presentation. It seems you have a very good mathematical analysis behind the work, and as I can see in the slides. Can you kindly show me your slides rapidly? Meanwhile, I should ask to other audiences if they have any question, please. Is there any question? Okay, so I ask my question from you, Mr. Ahmet. As you tested and presented us, you did this prototype with the 3 battery pack.
Yeah.
Yes. Yes.
Yeah. Please continue.
Yes, and as I can see from this figure, you should an adaptive inductor and LAC. Yes.
Yes.
So if you have any breakdown in your battery packs, for example, one of the battery packs is out of order and is broken out. So under condition, it seems that other packs need to enhance the voltage, and you need to enhance the voltage before connecting to the grid if you have a changeable inductance. Can you let us know what is your point of view for this condition for working mode?
Actually, there is no such scenario for fault conditions as you mentioned, but we can say that in terms of SOC balancing, there should be no problem again, but we need to just isolate this faulty cell first, faulty battery pack, and then if we need to make sure the total voltage of the remaining battery pack is enough for the grid connection. But if we,
also, you know, there is so many numbers of the small batteries inside of each of this package. So the breakdowning of any of these batteries is very possible. So I suggest you for your next studies consider this subject, and also I think under this condition the value of LAC should be changed, and you do not have the fixed value of LAC. Okay, please see your next slides.
Which one?
Slide number 68. Okay, here I can see a current fault after 0.5.
Yeah.
What is the reason?
And this is the actual point that we change active and reactive power references, and consequently active and reactive power of the system as well. And that's why there is such uncertainty in this moments. But again, it adapts to this condition and go on as expected.
Did you experimentally implemented this circuit?
Not now, but we have a project that we are currently working on. And
okay, very nice. Okay, very nice. I'm doing same studies, especially about the DC-DC converters and inverters and controller switching studies. I have too many papers, especially in the last 3 years in SCI journals you can find, and also you can join with me and with my group in my university. We can do some better studies, I think. Thank you for your presentation.
You're welcome.
Now, in turn, we have paper number 124, half bridge LLC resonant converter design for high voltage battery to low voltage battery conversion in electrical vehicles, and joint study from Istanbul Technical and Eskişehir Technical Universities, paper number 124. Mrs. Meltem
Yes.
Lordo.
Can you hear me?
Yes.
I will share my presentation now. Okay.
Okay, please.
Okay. Hi everyone. I'm Meltem Lordoğlu. I will present half-bridge LLC resonant converter design for high voltage battery to low voltage battery conversion in electric vehicles. This presentation will continue with scope and background information. In that part, I will mention about LLC converter prominent features for high voltage, low voltage DC to DC conversion system for electric vehicles. Then I will mention about methodology, especially about our design strategy in detail. Then I will share our obtained results. Finally, I will present our conclusion. Typical electrical vehicles consist of two main electrical power systems. One of them is the high voltage system and other is the low voltage system. The high voltage system is supplied from the high voltage traction batteries, which usually operate at DC voltages from 200 voltage up to 800 voltage, whereas the low voltage system supplies all the electric appliances such as interior lights, wiper, fluid pumps, heat pumps, air conditioning compressor. The new low voltage batteries operate at 48 voltage instead of 12 or 24 voltage. And on the other hand, this conversion from high voltage to low voltage needs to be efficient and safe. In this context, the LLC resonant converter brings solution these subjects with its great features like electrical isolation between the voltage levels and reducing the switching losses by zero voltage switching and zero current switching. The converter can operate at higher frequencies thanks to soft switching. Also, the converter can operate over wide output ranges, which is attractive for electric vehicles appliances. And also low electromagnetic interferences and high energy density are other advantages of this resonant converter. In figure, the parts of the half-bridge LLC resonant converter is shown. It consists of switch network, resonant tank, center tapped rectifier, and filter. And the first harmonic approximation technique is used in order to get mathematical relationship between input and output voltage. In this technique, only the first harmonic signals contribute to the power transfer is assumed, and the obtained voltage gain M is expressed in equation in terms of quality factor Q, inductance ratio KL, and frequency ratio F. In here, a step-by-step design procedure of LLC resonant converter with specified input voltage, output voltage, and output power is shown. The voltage gain equation is used to achieve the variable energy transfer and output voltage regulation. Firstly, transformer turn ratio is calculated for unity voltage at nominal input and output voltage. Then maximum and minimum voltage gain are determined. Selection of resonant frequency mostly depends on designer experiences. In general, below 150 kHz is preferred because EMI test starts at this frequency. However, increasing frequency provides advantage in the aspect of size of the converter. So in this application, 300 kHz is selected as resonant frequency. Then KL is determined for the maximum switching frequency below 400 kHz. Then Q values are determined so that the converter could give maximum voltage gain at peak load. After all maximum and minimum switching frequencies are determined using 6-degree polynomial equation roots. Finally, equivalent load resistance circuit elements as resonant inductance and capacitance and magnetization inductance are determined. After all, for controller design, small signal model of LLC converter is derived by using of the extended describing function method. In this method, the circuit variables are expressed as a sum of harmonics of the switching frequency. The equivalent circuit model is shown in figure. In here, LLC primary switch is modeled as voltage source, while secondary rectifier is modeled as current source. And there is one complex impedance due to the effect of switching frequency and one complex voltage source due to the perturbation of switching frequency in each resonant tank element. Here, LE, RE, CE represent the bit frequency dynamics. KV, GV, KD, and GD are the coefficients. These coefficients depend on the magnetizing inductance, and they are changed according to below or above resonance situation. LR is in series resonant inductance, Q is quality factor, and N is turn ratio of transformer. Finally, control to output transfer function V over WS of LLC converter is derived by using superposition method in order to regulate the output voltage. The proposed LLC converter is simulated by using power sim. Nominal output power of converter is 3 kilowatt. In the design, the input voltage can be varied 200 volts and between 200 and 400 voltage, while the output voltage is constant at 48 voltage. According to the design specification, LM, LR and CR are calculated like as here. And in figure, ZVC of Q1 MOSFET is shown. There isn't any current on MOSFET when the turn-on gate signal is applied, and the negative current flows through the body diodes. That's why turn-on loss of MOSFET is 0. The coefficients of controller, which are proportional Kp and integrator Ki, are found by using V over WS, by using V over WS, and the step response of the converter is summarized in the table, and no overshoot is not observed. With regard to output power variation, output voltage and current variation are shown top left of the figure, and the required switching frequency is shown in the top right figure. In accordance with the control design, it is seen that the output current increase and frequency decrease from maximum to minimum values, while output voltage is constant in case of changing load in every 50 milliseconds. Here, depending on varying input voltage from 400 voltage to 200 voltage, in every 10 milliseconds, the output voltage and frequency variations are shown in figures. In case of changing input voltage, output voltage is kept constant and frequency decreases to give same amount of maximum power. In this paper, a wide input range, regulated 48 voltage output voltage, adjustable output power until 3 kilowatt LC converter is proposed to be used as a DC to DC converter from high voltage battery to low voltage battery in electric vehicles. Different output levels are achieved easily by changing the load depending on the control algorithm. In addition, output voltage is provided constant in case of any voltage drops in the high voltage battery. Also, efficiency is further increased by minimizing the switching losses thanks to ZVC. Furthermore, it's aimed to maintain an inductive operation across the entire input voltage and load current range and fall never into the capacitive region operation. In the control algorithm, PI values are selected by using Mete PI tuner. The control algorithm adjusts switching frequencies to control the LC converter in case of load and or input voltage variations. Thank you for your listening. I will be glad to answer your questions.
Thank you, Mrs. Meltem, for your presentation. Now I want to get this chance to our panelists and other attendees. If they have any question, please. So I have some questions that I ask you to answer me. Please show me your slides number 3.
Number 3. Okay.
Yeah.
Maybe better.
So, as I found and saw from your slides, you are converting a prototype from, for example, 200 till 400 volts to the 48 volt with 3 kilowatt as your power, okay? So what is the reason that you are selecting a resonant converter? As you know, resonant converters really are complex to design because you are changing the frequency instead of the changing of the duty cycles. So this is really hard to be implemented. So what was the reason for this selection? It is very interesting for me to know.
Okay, actually, isolation is the best choice, I think, for in this application, because LM is the transformer component, but also it provides resonance. It attends to resonance in some conditions, and also maybe we don't change the duty ratio, but we can adjust the output power just changing the frequency. It also is, I think, but of course there is additional parts like switch network and rectifier parts, but also you see to this DC-DC system, first the DC to AC conversion, then isolation, and then AC to DC conversion. There is LC is similar to, I think, this.
Agree with you, but we have many kind of especially switch capacitor and switch inductor based DC-DC converters that easily do this, and they have not also they are isolated. Okay, I suggest you to
sorry, I can't hear exactly. I can hear clearly you. I don't understand.
I'm saying I'm saying, do you hear me? I'm saying that I suggest you to see many types of the DC-DC converters, especially the switch capacitor and switch inductor-based DC-DC and isolated type of converters without any transformer by changing the duty cycle instead of the frequency. So rapidly, can you show me your slide number 6?
Number 6, 3,
Yeah.
4, 5, 6. Right?
Yes, here. Yes, it's correct. Now this is 5, the next one. Yes.
6.
So at the third stage, you are talking about the selection of the resonant frequency. What is the criteria for this section?
Actually, generally, I look to literature. The designers just select the resonant frequency, but it is, of course, a very critical point for resonant frequency because it's directly affects the volume of the components and also electromagnetic interferences.
Okay.
But this I don't study over it.
Okay, okay. It's a good response. The volume of the converter can be a good idea for that. It's like 8 and 10 will be my final slides. 8 and 10.
8 here.
Yes. Here. Yes. And 10, please.
Okay.
Okay. Yes. It's rare that I found that your output voltage is fixed to 48 volt, and from this slide I saw that maybe using up a conventional DC-DC and isolated type of converter can be a good idea. Thank you for your presentation. And finally, we have the our last presentation with ID number of 156, a study from University of Tabriz, Iran, a novel multi-level inverter based on switched capacitor using units using improved H-bridge by, I think, Mr. Javad Nikui.
Yes, I'm here. Can you hear my voice?
Yes, brightly I can see and hear your voice and your face. Please, the stage is yours.
I'm sorry. I'm sorry.
You need to share your screen with us.
Yes. Yes. Hello, everybody. It's my honor to be here and this session. My paper title is a novel multi-level inverter based on switched capacitor units using improved H-bridge, and my presentation contents includes introduction, basic unit based on switched capacitor, and the proposed multi-level converter, and first comparison discussion, and if stimulation outcomes, and at the end conclusion. Nowadays, with the increasing development of the human societies and industrialization and improvements of the countries, the demand for energy has increased dramatically. Most of these energies are fossil fuels, but in recent years, for some reason, like pollution and other reasons, this kind of energy, I mean fossil fuels, have some problems. So renewable and sustainable energy sources such as photovoltaic and turbine have been recognized as a valuable substitution for fossil energy sources. And according to this issue, the use of power electronic converters have become more and more spread in this year's, and one of the most important power electronics are multi-levels. As all we know, the output voltage of the PVs are DC voltage. So if we want to use this kind of voltage, we should change it to AC voltage. So we should use inverters. And inverters and multi-level converters have some issues and problems. Some of them are lower voltage stress on components and lower distortion and reduction the filter requirements. But the main drawback of these converters is the excessive use of components, capacitors, switches, and other power electronic devices. The most, predominantly multi-level inverters are cascaded multi-level inverters, line capacitors, and diode clamp converters. And the most disadvantage and drawbacks of the diode clamp and line capacitor inverters are they use large number of diodes and capacitors to generate high level of voltage in their outputs. And the main disadvantage of the cascaded multi-level inverters is that they use DC voltage sources, and it costs more, and it's a disadvantage. In this paper, we use switch capacitor inverters to have more number of levels in our output, and we try to use less number of power electronic components to generate large number of output voltage. In this slide, basic unit based on switch capacitors is shown. This structure is ability to generate waveforms whose amplitude is greater than Vin, and it's because of using the capacitors. And as we've seen in it, we use two capacitors to generate more number of levels in our output. For example, if we have via in our output voltage, switches S2 and F3 are ons, and the capacitors C1 and C2 are charging. And if we have 3V in our output voltage, switch S1 and S4 are on, and C1 and C2 are discharging. In this slide, we have our proposed multi-level inverter for generating in the last slide, we see the circuit that generate only positive voltage levels. To have negative and zero level, we should have we should have insert H bridge to the output voltage, and in this study we insert improved H bridge to the circuit, and we have positive and negative and zero voltage. And with low number of power electronic components, we have more and more number of voltage levels in our output. And also the maximum output voltage is equal 3 multiple V in plus V in left side plus V in right side. And in this slide, we have a proposed general topology that we insert m number of I mean switch capacitor units to the left and right side, and we have a general topology. And with using this structure, we have the high number of voltage levels in our output, and we have a very soft voltage level in the output voltage, that it has low THD, total harmonic distortion, and it's good for us. One of the most important factors for multi-level inverters is standing voltage on switch, or SVS, which is the maximum value of applied voltage on the switch and in its output, in its off state. And we have and will be like the equations that I write it here. And finally, the total standing voltage of the proposed structure is defined as we show in the slide. In this slide, we have comparison discussion of this inverter and as we've seen, according to n level up into an IGBT and other factors. And as we've seen, our structure have low number of components according to n number of levels in our output. And one of the most important factors is number of DC voltage sources, and we have no number of DC voltage sources. And in the last section, we have simulation outcomes, and as you've seen, we use 50 voltage in left side and 200 for right side, and load, as you see, RL and LL, and the simulation results is here, and as we've seen, VO is very like and very similar to the sinusoidal, and IO also. And in the bottom we have output voltage in left side and in the right side, that by summing them, the main output voltage waveform is obtained. And in this slide, we have standing voltage on switches, and as we see the standing, it's clear that the highest standing voltage on switch is for switch SU, and it is equal to maximum output voltage, and we must use a high quality switch for this switch, and it's a very important note. And in the bottom we have capacitors voltage, and as we've seen. Capacitors are charged and discharged frequently by using series and parallel switching conversion. And it's for left side, it's 50 voltage, and for right side is 200 voltage, and it works very good. The simulation done for inductive load, and as we've seen, it is work good for inductive load, and there is no problem in it. And in the bottom we seen that if after emission of 1 unit, proposed converter can continue its own operation by creating 15 level of output voltage fed by single DC source, and it's that's reliability response of proposed converter, and we see it works and go, and it's we can see it works good, and there's no problem. Just the number of output levels is become low. And in conclusion, in this paper, a novel topology based on switch capacitor unit recommended. And when we compare to the suggested multi-level converter in other papers, we can see this structure utilize less number of power electronic components, and it caused reduce the size of the structure and simplify the control circuit. It was shown that proposed increase the input DC voltage by charging and discharging the capacitors without any using of transformers. So it decreased the cost and reduced the size. The main merit and advantage of the proposed converter could be flexibility to increase the number of the levels. Thank you for your attention, and I want to know if you have any questions. Sorry, I don't hear your voice. Sorry.
I'm sorry. I thank you, Mr. Javad Nekwi. So I want to ask to all of participants if they have any question. Please, you can raise your hands. If you don't have any question, I will ask my questions. So please kindly let me see your proposed converter structure.
This is slide.
Okay. And what is the your SC block, switch capacitor block, the internal circuit of the SC block?
It's sorry. It's here, one unit here and one unit here.
Okay, can you show me the internal circuit of the of these units?
Yes. Sorry. Yes.
This is structure. So, Mr. Javad, as you said us about the drawbacks of the existing converters, you said that
Yes.
they normally using too many devices in
Yes.
structures. But as I can see, your structure also use too many components,
Yes. Yes, it has many components, but we have so many, I mean, levels in output voltage. So we have low THD, and I mean, according to the number of levels, it has low number of components.
What is the power rate of the converter?
What is, I mean,
the power rate of the converter?
Power
the
rate.
level of the used power.
Yes, our output, I'm sorry, 1 minute. Our output voltage level is up to 700, I'm sorry. 750 volts.
Mm-hmm. Okay.
Yes.
And
we can see in simulation results.
Okay. Did you implement this structure in the laboratory?
No, we have no prototype.
Are you master student?
Yes.
Okay. So thank you for your presentation. I know you have worked and presented too many mathematical analysis for study, since I am professional in this field, and I have so many papers about DC converters, especially or inverters. So I know all of the drawbacks of the converters, and I'm dealing with this all type of converters. And also I know the lacks of the our good students in Tabriz in Iran, where in fact I'm an Iranian. Say my hello to Professor Dr. Said Hossein Hosseini. He was my professor when I was a bachelor student in Iran. Thank you for your presentation. Thank you for your great study. And thank you all because of your participation in this great and amazing conference, Electrical and Electronics Engineering conferences, subtitled ELECO 2021. I appreciate all of your studies and works in this session, and in all of sessions in this conference. And I hope to see you for next year, but this time face-to-face and not virtual in our Bursa. Thank you for your participation, and good evening.